So yeah, today my talk is optimizing graphics for mobile devices in Unity. So if you did go to the GCAP talk before, it's going to cover the similar topics. So my name is Brian Su, and I'm a developer at Not Doppler Games. So one thing with this presentation, I didn't actually optimize the length of it, so I'll have to probably skip over a bunch of stuff, but just bear with me. So let's just get started first. We're going to talk about our first in-house game, Crash of Cars, right? It has more than 25 million downloads, and it's been out for over 2 years now. So I think it's a pretty good case study because we face a lot of challenges. And from this, we learn a bunch of optimization techniques, and like I learned plenty new things too. So before we start, I'll show you a quick trailer. I know everyone wants to see nice graphics and stuff. So it's basically like a multiplayer car battle game, right? And kind of think of it as maybe isometric Mario Kart, lots of cars, hundreds of cars now, different weapons and things like that. So I'll just play a quick trailer about it, yeah. So you might recognize that hot dog car. It's probably on your stickers. So we started with a really small team, actually, only one developer and one artist at the start of it. We actually grew to 5 developers now. And we added in a whole different types of modes too. So like feel free to try out and stuff. We even added a mode that's kind of like Rocket League. So download it, and like if you have some feedback, just tell me about it. So about me quickly, I'm originally from the States, but now I call Australia home. I've been programming maybe for around 13 years now, both in Tokyo, America, now Australia, and probably been using Unity for 8 years, ever since something like 2.6, so I'm pretty old, and self-taught graphics programmer and the first person on Crash of Cars. That's me. So before we start, I want to just talk a bit about optimization. This is how I kind of think of it in my head. So just the amount of memory you use times how much CPU or GPU you use gives you performance. So if you kind of rewrite that equation, the more memory you throw at something, the less processing power you need. And same vice versa, the more processing power you use, the less memory that you need. So one kind of concrete example of this could be something like light maps versus real-time lights. So light maps, you bake everything into a texture, and when you're running the game, the only thing you need to do is read from that light map, as opposed to something that's doing like all real-time shading in your shader, like shadows and things. That's more the processing power. So most games, they try to strike a nice balance in between the two. But for mobile devices, like even old ones have heaps of memory in them. So I kind of want to skew it more towards the memory side. So try to use more and more memory to reduce the amount of processing power you need. So if you're ever stuck in a situation, try to think, like, what can I cache? Can I write this into a texture? Can I make this into a lookup table or something like that? So just think about that first before you actually try to micro-optimize everything. So what we're going to cover today is mostly about, not about any kind of script side, like garbage collection thing. We're mostly going to focus on GPU stuff. So mainly 2 kind of important points, vertex count, and also fill rate. So those are your 2 kind of enemies when you're dealing with mobile devices. And for this talk, I'm talking about really old devices like maybe iPhone 5, which are equivalent to a lot of devices people use on Android now. So if you kind of think about the global market, like we may have really advanced phones, but if you go to other places, they might have like just older, cheaper phones equivalent to only like OpenGL ES2 stuff. So you do still have to consider it a bit. So brief overview, we can talk a bit about terrain shading, how we did shadow blending, and something called immediate drawing I use to render blob shadows, and also improve UGUI text overdraw. And the quick tips about reducing UI fill rate, shaders in Unity, and finally, profiling in Xcode. And if time permits, which I doubt, like I'll talk about some fun stuff. But this part's fun too, so don't worry. So we're just going to talk a bit about the terrain shader first. So when we made the terrain shader, we didn't make it a surface shader. So if you don't know what surface shader, it's kind of a high-level way Unity uses to describe a surface. So all you do in the shader is say, I want this color albedo texture. I want my normal map to be this and that. Then Unity handles all the nitty-gritty details for you. It calculates the lighting and the shadows and all those things for you. So it's great, but it causes a lot of unknowns. So, and those unknowns are also performance unknowns. So what we do is we don't use surface shaders. Then you know exactly where your performance issues are coming from. So we do lighting in the Vertex shader. A lot of people say this, but the reason is if you do lighting in the Vertex shader, it stays at a constant cost, right? It depends on how many vertices you have. If you do per pixel lighting, it actually depends how many pixels you're rendering on the screen. So it's per vertex. It doesn't matter how high resolution your screen is because you're doing it only per vertex, not per pixel, right? So we only use one directional light and a shadow map and 4 unique terrain texture types per mesh. But that's per mesh. So if an artist actually wants to use more kind of terrain textures, they just split up the mesh. And at the time, we only have one artist. So we actually use shader-based UVs. So because there's too much effort to basically texture UV map every single piece of terrain. So if you ever UV mapped a bunch of hills, you know how hard it is when you're stretching the UVs. So here's a basic breakdown of it, right? It's a pretty simple shader, bare bones. Like you have a splat map, and all the splat map does is determines where textures go based on the color of the splat map. So red can be grass, and green can be rock, and blue can be snow or something like that. Then we also have a shadow map. So this is a shadow map we bake into Blender. It's a bit different from light mapping because we're not using UVs in this case. Using those two, we kind of get that result. So when you're kind of texturing terrain and not using UVs, the only procedural texturing methods you can do through the shader are a bit limited. So one of them is triplanar shading. So this is the first thing we did, right? So if you don't know what triplanar shading, it's basically sampling the texture in 3 planes, like the X, Y, Z plane. And all you're doing is taking those 3 texture samples and just weighting them based on the surface normal or the surface curvature. So if you look at the sphere above there, you can see how everything blends in on the corners. So this is a great technique, no stretching, works on any shape and things like that. But if you look at the code, so I'll be referencing a lot of code, and I may go through it quick, but you can grab the slides because there's a lot of code in here you can actually use. And you can see text 2D, text 2D, text 2D. That's 3 texture samples just for each unique texture. So what happens when you have 4 unique textures? It goes up by 12 times. So sampling the textures 12 times in the shader isn't good. So we kind of looked at our game, and it's an isometric game, and it's primarily on one plane, so it's kind of a 2.5D game. So all we basically did was just take one of those planes, the flat horizontal plane. So it still looks pretty good, like that, and we still don't need to manually unwrap the UVs. But of course, the issue you get with this is any kind of vertical or very steep wall, you get that texture stretching. So what we did was the simplest thing. We just covered it up. But this is a very good point because often you'll give your artist something, but a limitation, and if they work hard and are good at it, they'll often get around it. So just trust them, give them less at the start, and you'll see what they'll come up with. So if you didn't understand exactly, this is how it happens with the texturing. It's basically a one-to-one mapping from the texture to the actual physical world. So if you took the UV coordinates, minus 0.5 because UVs go from 0, 1, and you multiply it by these world bounds, you get the actual world position in the texture. So just think of it if you had a big projector and you're just projecting that texture down. So with how we actually generate these shadow maps is we actually set up the scene in Unity, but after that we actually exported it back out into Blender. So we had a tool to convert it to FBX. Then what artists would do is they would bake shadows and ambient occlusion and bring that back into Unity. Yeah, and that's the result. So it looks pretty nice, and you can't really see any of the stretching because, yeah, it's all been covered up like that. So now I'll talk a bit about shadows. So in our game, we have 3 types of shadows. First one's for dynamic objects. When you're using shadows from dynamic objects, if you want your shader to receive them, you use a macro called light attenuation with a little bit of setup. Then you can receive shadows from objects through Unity. And another type is the static shadow map, which I mentioned before, and the third type I'll talk to you about later. So in order to blend that kind of dynamic and the baked shadow map, since it's only a 0, 1 kind of black to white shadow value, all you have to do is multiply them together and you get that. So it's pretty seamless. And even though the real-time shadows are hard, I reckon like most mobile people, they won't, when they're playing the game, won't say, oh no, your dynamic objects don't have soft shadows or something. I've never seen that complaint on Google Play yet. But we also use something called smooth step. So if you don't know what smooth step is, it basically maps a value on a Hermite curve. So I hope you can see that. There's a green line, it might be a bit faint, but basically that red line, pretend that's like a linear shadow. Color is going from 0, black to white. So it's remapping that to a curve. So in your function right there, the 0 and 1 on the left side 1, that basically describes a start x and the end x of your curve. So if you put 0.5 in the second one, it actually squishes that curve. Then anything above 0.5 gets mapped to 1. And if you put 0 in there, eventually you only get anything greater than 0 will map to white. So you can see how the shadow gets more harder and crisp like that. So it's a way to actually, if you wanted like crisp shadows or soft shadows on your baked shadows, that's a way to do it. So I mentioned before about world space UVs. So one cool thing about this is like all you have to do is sample the world space position of your object and sample that world space light map. So what happens now is that actually projected light map gets on your real-time objects. It's not physically correct, but most people won't notice. And if you don't quite understand what I mean, so here's a car right here. It's going in and out of shadow, and that's using a baked shadow. But when you lift it up, you see it doesn't actually go out of shadow. So kind of projected 2.5D shadows. The final combined result, you have real-time shadows and baked shadows mixing together, and the baked shadows casting on a real-time object. Another quick tip you can do is in our game, we actually don't use the actual model as shadow casters. We actually use a proxy, so a low polygon model. And all you have to do in Unity is set to shadows only mode. So next, sorry, I know I'm rushing through everything because there's quite a lot of content, is immediate drawing. So immediate drawing is basically a way to render into a texture without a camera. So usually when you render an object, you have a camera, you add a render texture to that object, and you render what you want inside of that camera. But I wanted something more analogous to set pixel, something very easy to draw, like shapes and pixels like that. And for me, it's very annoying to have extra game objects like cameras and cubes just to render certain sprites. So what you can use is these kind of GL and graphics draw mesh now commands. So GL is pretty similar to, if you know OpenGL, it's pretty similar to that. And you can use these to basically render out individual triangles and quads. You just specify like certain vertices, and it will render out a quad for you. And draw mesh now is a way, if you don't want to do that, you can render entire mesh using that. That will render directly into a render texture. So I'll show you the code for it. So this is all you need to do to actually draw into a render texture. So you get your render texture, you set it as a target, right? So that's your canvas. Then I clear it. I clear the color to black and depth too. Then I push matrix. Push matrix saves your old camera matrix. Then I call something called load ortho. So you have no camera now, so you have to actually choose a projection matrix for this. So load ortho just creates an orthographic projection going from, I think, like 0 to 1. And this is perfect for drawing just like 2D shapes and things like that. So as I mentioned before, like no game objects to manage, no camera overhead. I think there's another talk talking about a bit. And it's perfect for drawing simple shapes. If you've used set pixel and get pixel and things like that, you know it's kind of slow. So think of this as like a GPU way to render into a render texture. So one example is it could be a sine curve right here. Same exact code, but only code that's changed inside is that little for loop there. For every point on that sine curve, I'm just drawing a dot. And then we can render whatever we want with that. So fast way to render pixels to a render texture. So what are the uses for this? Basically, we use it for blob shadows in our game. So we have a low quality mode in our game. If it detects that your device isn't that powerful enough, it actually won't render any type of Unity shadows. So it will look like this, but we still needed some kind of reference point when you're playing an isometric game. So we rendered blob shadows under the cars, and we just render blob shadows and blend them with the big shadow map. So why not use a projector? So if you've used a projector before, what happens is Unity actually re-renders the mesh that it's projecting on. So if you had a big terrain chunk and a character with a blob shadow projector, when that shadow goes over that terrain, it's rendering it again. And imagine if you have 10 characters, each with their own projector, it would have to re-render that terrain over and over and over for that projector. Same with the shadow quad is, you can use a shadow quad, but it's always hard to align a quad to the terrain perfectly because you're constantly mesh ray casting, and your little shadow quad won't align perfectly to all the bumps and the grooves into the terrain. So what we did with the immediate drawing is, so for each car, we just have to pass in, you have to remember we're using world space UVs, so those UVs can map directly to the texture. So we just get the world space position of a car and make it 2D by taking out the Y position, and we render a blob at the position where the car is. And you end up with a texture like this. It's just a bunch of blobs. Each of those blobs are a shadow. Then all we have to do is just blend it back in with that big shadow map. And this is a result. Oh, so that's the projected texture on the world space what I was talking about. And you can see right here. So this was only for 10 cars, and I think the CPU overhead was very low for it. So we could technically render probably 100 shadows and wouldn't be much of a performance. To make it a bit more robust is, like if you render a blob shadow, you'll get a projection that goes upwards. So if there's geometry above it, you'll see the blob shadow. But you can do other things like we actually can encode the height into the green channel. So you can see height, I do plus 10 divided by 20. I'm just normalizing a height from negative 10 to 10 to 0, 1 range. Then in the surface shader, I can pull out that green channel, and that tells me what height the car is at actually. And I just compare it with the terrain height. And if the shadow height is higher, terrain height is higher than shadow, I just don't render the shadow. You can also use this for things like fall off and things like that. So it can work more in a 3D space. So other things you can do with it, I've done, you can render dirt tracks to that world space texture. Even use it to displace your terrain. So if you have like some snow game and you're driving your car around, you can render little quads behind that car into render texture and use that to displace your snow and things. Even bake in like 2.5D fake point lights. So another thing we used it for was caching UI, okay? So maybe a lot of people of you have like a game where the user can put in their name and things like that. And in our game, we mostly use TextMesh Pro because it renders a lot of things really nicely. But the issue with TextMesh Pro currently is that you have to know every single character that's going into your game because it has to pack it into a character atlas to use it. So you have to use UGUI text because UGUI text currently is the only one that supports dynamic font generation. I have heard that Unity is working on dynamic fonts for TextMesh Pro, so maybe it'll alleviate the problem. So here's a bit of UGUI text, lorem ipsum right here, and it's not bad. You can see it's like 500 tries and 1,000 verts. But to make our text nice and look like what it looks like in TextMesh Pro, people will add outline and a drop shadow. So what happens when you add that? your tries go up to 4.6K and 13.9 thousand verts. So you can see why, because it's just taking the text and rendering it 4 times for the outline and the drop shadow. So it's not only a vertex count issue, it's also a fill rate issue because it's re-rendering that same text over and over and over. So if you're making some game like role-playing game that has a lot of text all over the place, you can bump up your vertex count a lot and cause fill rate issues. So how can we optimize it, right? So usernames, they can't stop the game in the middle of a game and change their username. They only do it through the meta, the main menu. So we thought we can just bake it into a texture. So what you can use is there's a class in Unity called Text Generator. And what Text Generator does is it lets you input some text, then it will spit out all the vertices and all the UVs you need to actually render that manually. So here's some code right here. So source text right there is just Unity text, and bounds of the text is kind of the bounding box you want to render the text in. So what will happen is you just call that function get generation settings, and that will return a settings file. And you pass that into your generator and along with what text you want to render. So what happens, it generates all the UVs and vertices, and you can use get vertices. So once you have the vertices and the UVs for your text, you can use the same direct drawing, the same code. Just grab all those vertices and UVs, and use the geo commands to draw directly into the texture. The material I use is actually the one in the font material. So if you open up your font, you'll see a material underneath it. And yeah, I could actually use geo quads there, but I use geo triangles for some reason. But what happens is, yeah, you can bake text into a texture. So now it's only a single transparent quad. And to make it look nicer, we actually did a 4 to 8 tap outline filter. So I actually put the code down here. So I won't go through it, but you can reference it later, copy paste it if you want. So another good thing is that now it's a texture, so you can do per pixel effects like sine curves and shiny stuff like that. So I want to talk a bit about reducing UI fill rate. So one common UI design is a panel. So I'm assuming like everyone has at least one panel in their game or something like that. So most panels are just a kind of a decorative border along with some fill right there. So what you can do is kind of split those two up. So in Unity on your image component, you can tick off fill center and it will just render the outside part. Then in the second part, what you do is you can grab the UI shaders, the built-in shaders, and modify them by taking out Z-right. Let me do that again if you didn't see it. Z-right and blending. So what this is basically doing, it's turning a UI from a transparent shader to a solid shader. So anything that renders behind it won't be rendered. So you have to know that even if your image is fully opaque and it has alpha 1, it's still a transparent object according to the UI. So you just put those together and you can remake your panel like that. And with I did some profiling, and for 10 full screen pop-ups, you can see we dropped from 3.35 milliseconds to 0.79 milliseconds. This will be a lot worse on older devices like iPad 3. So some other things you can do, like if you don't use scroll recs or with masking, you can actually remove code related to stencil masking and alpha clipping. If you don't need to tint your UI, you can even remove that kind of code. So every single bit can help, and there's actually a link there from Unity that shows you how to make a bare bones UI shader. So don't be afraid to modify the UI shader. There's nothing too magical going on in there. It's not like looking at the standard shader with 1,000 lines of code. And just be careful about UI because it's very fill rate heavy, and it will affect devices like iPad 3 a lot. Even just one kind of transparent overlay will drop your frame rate. So this kind of technique is not only for UI, you can use it for anything. Like another example might be you might have a cloud sprite, but the only transparent areas are around your cloud. So you can actually cut that out into a separate mesh and have a solid center, and that actually reduces your fill rate. Yep, and Next, we'll talk about shaders. So in our game, 90% of shaders were all custom shaders, and we try to avoid surface shaders, but a small amount of them were surface shaders, and one of them was a car shader. The reason behind that is probably because I started it as a surface shader and never changed it. So basically what we did is we kept it very simple, right? We compute specular in the vertex. So often you'll see games computing specular in vertex because that uses very expensive things like power functions. Power and trig functions, all those things are quite expensive in pixel shaders. Then we calculate just a simple ambient ourselves, which is just like a ground color and a sky color, and we combine them all together. So for kind of higher tier cars, we wanted to make them look a bit shinier. So we didn't use cube maps. We actually used something called matte caps, or kind of spherical environmental maps, right? The reason behind this is it's 1/6 the storage of a cube map. And if you use less storage, you can actually make your reflection texture a bit higher res. So yeah, it's a fast technique, and I think it's very easy to author, and you can kind of understand quickly just by looking at that, like what your reflection is going to look like. So it's good for things with a lot of curvature and things like that. But yeah, just give it a try, I guess. So with your surface shader, right, you can optimize a surface shader too. So one thing Unity lets you do is it actually lets you use your own custom lighting. So if you put something in there like pragma surface custom lighting, you can write a function called lighting custom lighting. Then Unity will actually look for that function and will use that to compute the lighting. So in our case, the reason we did this is we don't want to compute specular lighting inside the standard lighting equation. So what we did was we only created a custom lighting function and only do diffuse shading inside of that. And we did all the specular outside of that in the vertex shader and just passed it into the emissive. Hope that was understandable. But so other useful things you can do is Unity has a lot of things you can add in to help optimize stuff. So one is interpolate view, and that basically says I don't want to calculate the view vector per pixel, but I want to move it into the vertex shader. And I guess, excuse my language, half-ass view. And this basically computes a half vector. Half vector is basically used for specular lighting. So move some of the computation back into your vertex shader. So you don't have to really understand that, but you just try putting these into your surface shaders, and you might get a bit of optimization. So another thing is no ambient lighting. So what Unity does now, if you use a cube map for lighting, the actual ambient lighting is calculated from something called Spherical Harmonics. So if you don't know what Spherical Harmonics are, you can kind of think of it as something called compression, right? So it's compressing your cube map into a bunch of numbers. So in the case of Unity, like 9 different numbers. So what Unity does is it uses those numbers and computes some of the ambient light in the vertex shader and some of it inside a pixel shader, and combine those together to create the final image. So if you put no ambient, it kind of takes out that bit of overhead. So there's a lot of these pragmas if you look on the surface shader documentation. So another thing you can do is toggle features. So we use this a lot, and you can do it by adding multi-compile or shader feature. The difference between these two is multi-compile, right? Always keeps those shader features inside, but your game. But shader feature actually calls them out if they aren't used in the material. So the reason why you would use multi-compile is you might set shader keywords in your code and stuff. And Unity can't detect, oh, I'm using this keyword, but setting it in code only, so it'll try to strip it out. So it's a really good technique to minimize features you don't need, but it creates a lot of variance. So I also added a link down there that you can actually use to calculate how many variants that your shader will produce. So if you want to actually go into it and inspect it a bit more, you can just click on the shader and just click that down arrow there, you'll see a show button there. So if you click that show button, what will happen is it will list every single variant that your shader is using. So you can see, well, it's probably hard to see on the top. You can see keywords stripped away when not in use. So these were the keywords I put under shader feature. Then the next line says keyword always included in build. Those are the things I used with multi-compile. So it shows you it shows you a breakdown everything that's being used. So if you don't want a feature to be used in your game, you can use a pragma called skip variance. This will guarantee, no matter what, that Unity will strip out these features that your shader doesn't need. So just to give you an idea, a standard surface shader that's stripped has 52 variants, but non-standard one has 2,000. So, and I think the actual standard shader itself can have something like 20,000 variants. So you may see, like when you open a project, you may see a shader compiling line going for a couple minutes and stuff. That's because there's so many different types of variants. So some other tips too. Expensive stuff in the pixel shader. Avoid things like power, exponential, and trig function. And older devices, sometimes they don't like conditionals like this. But you can actually rewrite any kind of conditional branching using step functions like this. And also be careful of things like older devices using things like text 2D, LOD, texture arrays, and texture 3D. A lot of that is not supported. So if you want to target the bare minimum, don't use these things. So now I want to talk to you a bit about dependent texture reads. So one thing a lot of people often do is they'll get UV and they'll scroll it or something like that. So you can see right there, like main texture, IUV plus some scroll offset. People often do this inside a pixel shader, but it often causes something called a dependent texture read, which I'll kind of explain in the next slide. So it's better actually to move, if you can, move these UV calculations into the Vertex shader. But there's cases where it's a bit harder when you use like another texture to distort another texture. That's often used as something like a flame texture with distortion. In that case, you just kind of have to minimize that. So dependent texture reads, right? Originally, I thought too what a pixel shader does is just takes the data from the vertices and gives you interpolated points. But what it actually does, is the pixel fragment shader does, is samples a 2x2 area every time. The reason behind this is it calculates something called gradients. So all gradient is finding the difference, a dx, dy between. The reason behind this is it uses that information for things like calculating bitmaps. So if it knows those two pixels are really close together, that means use like a lower bitmap, and if they're really far, I think that's opposite, but really far away, use a higher bitmap. So this all happens in the background, like you don't notice it. So the issue with the dependent texture read, so you're modifying UV in the pixel shader, right? It doesn't know what its neighbor is when you do that. So it can no longer calculate those gradients efficiently. And that's why you should move your UV calculations into the Vertex shader. Move everything in Vertex shader, but be kind of careful. Like position offsets and scales are okay, but if you do something like a sine, cosine value, then it doesn't work that well. It depends on how tessellated your mesh is. And remember, shader complexity is not always just what's inside a shader. Consider how many pixels are being rendered, and along with how many vertices you have in the model. So it's not easy as just directly looking at the code. And yeah, be careful of shader variants. They can consume a lot of memory. Like, I think in bigger projects, you can consume hundreds of megabytes. So just be careful about that. So I was going to talk about the frame debugger, but I might skip over it because I have a lot of other stuff to talk. So I'll just talk about one thing. So with your frame debugger, I use it actually to analyze the draw order of things. So it's actually better to draw things with simple shader first than complex shaders later, because the reason is when something simple gets drawn first, it'll write to the Z buffer, then the complex one won't run. So this, I think, even affects things which are not transparent. So finally, I'll just talk a bit about GPU profiling inside of Xcode. So you can use a Unity profiler, but it runs into a few problems. Like if you're a Mac user, you'll see often not supported because of OS issues, and there's like editor overhead, and your device doesn't match the actual hardware that you're deploying on. I know you can actually attach a debugger remotely, but Xcode gives you a lot more detail. So I'm just going to take you through a scenario of how you can kind of look at your shaders. So first, start your project in Xcode, right? And have it running on your device. Then find a place where it's kind of heavy. Then what you're going to do is click that camera button, capture GPU frame. 50% or maybe 70% of the time it's going to work. Other time it might crash your device, but just go with it. But usually the reason is your app might be using too much memory. So it'll pop up this thing. So it's quite a lot of things to look at and kind of take in. So I'm going to try to break it down piece by piece. So on the left side is kind of your commands that are going in. Kind of think of it like all your draw calls that are happening currently. Then on your right side is kind of your screen buffers. So this shows what has been drawn up until that current command. So if you keep toggling through all the commands, you can slowly see your scene getting built up. And you also have depth buffer and stencil buffer if you want to look at that. So in the middle, it will show all the resources that the command is using. So that command is drawing using these textures, these shaders, these meshes. And you can actually inspect each of those elements. So if you want to kind of analyze some shaders, what I usually do is I click the FPS button. What that does is it brings up a list of all the shaders used for that current command, and it's sorted by how much GPU percentage it's using. So what you can do is we'll just analyze the most expensive ones. There's Blit, Copy, and World Space Terrain Fast. So let's just ignore Blit Copy for now because yeah, it's not really relevant at this time. So what we're going to do is we're going to open up that World Space Terrain Fast, and it's going to list all the commands that are using that shader. So along with it, a percentage of how much that GPU is using. So we see command number 211 is using the most, 23.3%. So what we do is we go back to that list and we find command 211. They're all numbered on the side. So what I first do is I kind of visualize what's happening between that command and the command before. So I look at the screen buffers right there, and I just kind of toggle between them. So you can see why it's expensive, because it's drawing that huge terrain chunk right there. And I mentioned before, shader cost is not just what's inside a shader. Even though it's optimized, it's rendering a lot of pixels. Yep, that's what I said. And so how do we analyze this? So we go into our resources box right here, right? And we're going to find that shader. So it has two segments, one vertex and fragment. So under the fragment, you'll find a file called xlotmtl main. So that's the shader that Unity has converted into a metal shader. So you can double click it and you'll see this pop up. It's a code. And along with it, you'll actually highlight the expensive lines of code, and you can see a percentage next to each line. So you can see how in-depth it is. So we'll go to one line of code right there. And it's taking 13.13%. So just as an example, what we can do is we can actually delete that line and save the file and reprofile. So the great thing is you can edit the shader code runtime, and when you hit that reprofile, it's going to profile that same exact frame, but with your shader changes. So you just go back and click your FPS again, And now you'll see two graphs. So blue was what was before you modified the shader code, and green was what was after. So by deleting that one line, it dropped down to 1.96 to 1.55. It's not a lot, but that's the basic process you can do to kind of modify your shaders. And the reason like I do this, it's very fast for iteration. So if you think about it, what I did before was modify the shader, build, then you have to wait 10 minutes. Then, oh, this is slow. I have to go back into Unity, modify the shader, build 10 minutes. But in this one, you can keep iterating, modifying that shader. There are a lot of other tools Xcode provides, like things like to simulate like lower texture fill or simulate wireframe mode only. So if you go into a bit more detail, like or read the documentation, it can be quite helpful. I think when people kind of profile and they use that GPU frame capture, it's just too much for them. But just as a starting point, try doing this. It's pretty simple. Click the FPS, find your most expensive shader, and just analyze it. Even if it's just looking at that list of shaders, like it will help you out. And you're running on real hardware, so these optimizations really reflect what's happening, and you look hardcore doing it. Good for time. So work closely with your team, obviously, and don't try black box things. Like even with your artists and designers, try explaining them all these technical aspects. They like to soak up all that information, and like make a lot of tools, and you'll be surprised with what your artists and designers come with. And just kind of think optimization is always this kind of tug of war of like memory versus CPU and GPU. So when you're in kind of a bind and your frame rate's like 10 frames per second, just think, can I use memory somehow or cache something in that case? And there's a great link right here for Unity about performance optimization. Yeah, thanks for listening. And anyone have any questions? Yes. Yeah, initially we only used Blender, but we're now a mix of Blender and Maya, and things like that, because it's kind of hard to find Blender artists. Anything else? So just quickly, if you do get the slides, there's a lot of bonus stuff here, like how we did, rain effects, then a lot of other fun stuff like height fog, and kind of screen aligned particles, then making your own baked shadow maps. And yeah, you can see why I said this presentation was not optimized. And something called baked volumetric shadow maps. Those are my awesome drawings. But so after this presentation, like I recommend you get it and just look at all the reference stuff, because I can't have part 2 of this presentation today. Okay, thank you.